Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to discuss techniques that allow deep learning and Q-learning to work together. Previously, we discussed that you actually already have all the tools you need to implement Q-learning with a deep neural network. Remember, our update equations are in terms of arbitrary gradients, and therefore you can use any model you want as long as you can differentiate the output with respect to the parameters. And of course, you don't need to derive the gradients by hand, since Theano and TensorFlow have automatic differentiation. So I hope by this point, you've tried this at least once and have seen firsthand that it doesn't seem to converge to a good solution. So in this lecture, we are going to discuss some modifications we can make to the basic Q-learning process that will make this work. First, you may have heard of the term deep Q network. You may have wondered, how is this different from a regular deep neural network? Well, it is in fact not at all different from the stuff we've seen so far. Really, it's just a regular deep neural network that we are using for Q-learning, or in other words, it's being used as a function approximator for the action value function. There is an important subtlety that we have already seen in our implementation of function approximation for Q. And that is, rather than transforming the state-action pair into a feature, we instead transform only the state into an input feature, and instead have multiple output nodes, each representing the value for a different action. This is a deep Q network, or DQN. The next trick we use is called experience replay. I've alluded to this multiple times in the past. You can think of Monte Carlo methods as a tiny step towards experience replay, because when we use Monte Carlo, we obtain a set of state-action return triples that we then use to train the function approximator all at the same time once the episode is over. With experience replay, we take this a step further. We introduce what is called a replay buffer. The size of the buffer is chosen by the programmer and is considered to be a hyperparameter. Inside the replay buffer, we store 4 tuples of state, action, reward, and next state. To train the deep Q network, we sample a random mini-batch from the replay buffer and use that as training data. The buffer basically acts as a queue. In computer science terms, that means first in, first out. So the buffer always contains the most recent 4 tuples. By taking random samples from past experience, we get a better representation of the true data distribution. This is better than the default Q update, where there can be hidden patterns and correlations that will affect how the neural network learns. Imagine if you are trying to classify pictures of animals, but instead of your training data being evenly distributed animals, you first only have cats in your first batch, then you only have dogs in your second batch, and so on. This wouldn't work very well. Since Q-learning happens on every step, you might be wondering what happens at the beginning when there hasn't been any actual experience to replay. The answer to this is that initially, we store random experience in the buffer. For instance, you can keep playing episodes and doing random actions until the buffer is filled. The next trick is related to something we learned about in the previous reinforcement learning course. Recall that Q-learning is a temporal difference method. Temporal difference methods use the value function itself as the target return. This is weird because in regular supervised learning, the target is always given as part of the training data. You would never have to estimate it. Because of this, when we do gradient descent, it's not a true gradient. We call it a semi-gradient. For deep Q-learning, this also leads to instability. The solution to this is to introduce another deep Q network. We call this the target network, and as you might suspect, this network will be responsible for creating the TD target. The target network is essentially a copy of the main Q network, but it isn't updated as often. So for example, you might make the target network constant for 100 time steps while continuing to update the deep Q network. Only every 100 steps, you'll copy the parameters of the main deep Q network into the target network. This helps stabilize the targets. The next technique isn't a trick per se, but it has something to do with the fact that the states are raw pixels of the screen. These are images, of course. As you know, the way we deal with images in deep learning is to use convolutional neural networks. One problem with still images that I showed you in the introduction is that you can't tell how things are moving. For example, in Breakout, you can see the ball, but you can't determine its velocity from just one image. Therefore, we can't only use just this one image. But remember what we learned about in the last reinforcement learning course, about why the Markov property, which may seem limiting because it says that the current state depends only on the most recent previous state, is not necessarily limiting since we can be the ones who define the state. In other words, suppose you are using Markov models for next word prediction. You are given the word the, and you are trying to predict the next word. This is of course not an easy task because many words can possibly come after the. One solution to this is to use a higher order Markov model so that the current word depends on a few previous words rather than just one. Another solution is to simply define each state to be 3 or 4 words in a row. So now the previous state would be the quick brown fox, and we pretty much know that the next state is going to be quick brown fox jumps. So this is the same thing we do in deep Q learning. We use a convolutional neural network, but instead of using just one most recent frame, we use the previous 4 frames. In addition, we also convert the image to grayscale, since as you can imagine, color information isn't that useful for games. So we start out with a 4D tensor where the dimensions are frame number, height, width, and color. And we take the average along the color axis, so we end up with frame number, height, and width. This is a 3D tensor, but we're already used to working with 3D tensors in convolutional neural networks because the third dimension is usually color. Now we're simply replacing color with time. This is irrelevant from the perspective of the neural network itself, since all it sees is a 3D tensor and it's doing convolution along the width and height dimensions. But it's nice to know that we already have all the tools we need. We don't need to build a special kind of convolution or anything like that. So let's do a summary of all the modifications we just talked about. First, we are going to build a deep Q network where each output node corresponds to a value for a specific action. This is as opposed to considering the action as an input into the neural network. Second, we store 4 tuples of state, action, reward, and next state in a buffer that we randomly sample for training. Third, we use a target network that is a periodically updated version of the main Q network. This target network is for generating the target for the TD error. And finally, we are going to use a convolutional neural network with grayscale images and the past 4 frames to represent each input state. So what's interesting about these changes? Well, each of these changes isn't anything particularly challenging to implement. You know how to create a neural network with multiple output nodes. You know how to store things in an array or a list, which will be our buffer. You know how to build a convolutional neural network. The only interesting challenge is making a copy of a neural network, which is something we haven't done before. As always, I recommend trying to build this yourself first, since all of these things are within the limits of your skill set at this point.